Hello and howdy, ladies and gentlemen. In this video, we are going to be taking a look at question 25, the last question. We're going to be finishing off our 2019 Cayley paper. What have we got for question 25, our very last question? For how many positive integers x does there exist a rectangular prism, PQRST UVW, labeled as shown, with PR, this diagonal down here, 1867, the year Canada became a country. PV, 2019, the year of the contest. And PT, this diagonal over here, X. And so X is a positive integer, otherwise we'd have lots of possibilities. So they're giving me not the dimensions, but some diagonals. And they're saying what are the possible other diagonals you could have in the wide universe of possible prisms, rectangular prisms we could have. Okay. So, noticing that these are diagonals, I mean, how do you find the length of a diagonal? For a rectangle, well, you use the Pythagorean theorem. So say this one here, 2019, you know, this is a nice little right angle on the flat side there. Okay. And then we've also got 1867 along here. So if we use a nice little right angle in the corner here, we can get 1867 as the hypotenuse of a right angle triangle. And then over here, on the back side, we've got x. And we can see it's also part of a right angle triangle. It's the hypotenuse of a right angle triangle. So if we give names to the dimensions, normally I'd use something like x, y, z. They've already used an x. So we could say, you know, A, B, and then the long side here is C. I can see there's an A back here. This is a C. So we'd get, what, x squared is A squared plus C squared. 1867 squared is this front triangle with A squared and B squared. 2019 squared is B squared plus C squared. All right, so a nice set of equations. Now I've got 3 equations and 4 unknowns, which is good. I shouldn't be able to solve for x, but we do want certain values for we want the possible integer values for x. So what can we do? Well, I'm tempted to add all these equations up. 2019 squared, 1867 squared, and x squared should be equal to 2a squareds, 2b squareds, and 2c squareds. Now we're interested in x, so let's change these a squareds and c squareds to x squareds. Then you can cancel an x from both sides. I'm going to bring this unknown b. Now, we can make the boxes, you know, really thin and long if we need to. There's a lot of variability there. But one thing we can't make is we can't make the dimension be 0. So cancel out an x from both sides. We've got a formula here for x squared. We're saying x squared can be anything as long as it's less than, strictly less than 2019 squared plus 1867 squared. So we could say something like that. So b is a length. So b is greater than 0. So 2b squared is greater than 0, but they didn't say the dimensions had to be integers or anything like that. So b could be very, 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 very tiny. And, you know, very tiny, but go long that way, high that way. Everything could still work out, right? So what we've got is x squared is less than 2019 squared plus 1867 squared, which is, I don't know if we need to calculate it now, but 2019 squared 1867 squared. That's a big number. And it's so about 7.5 million. But if we square root both sides, I'll get x has to be less than. Oh gosh, what is the square root of that? Square root 7562050. So x has to be less than 2749.91, but x is an integer, so x can at most be 2749. There should be a way to pick a b and so on to do that. Right? But there should similarly be like a lower bound. If you make b narrow enough, that's fine, but you should be like, as soon as I figure out an x, in theory I should be able to solve for all the a, b's, and c's and get the right rectangle. Now, is there a way we could get sort of a lower bound for x? Maybe say x is something plus, not b squared, but maybe c squared or a squared or something like that. C squared's got to be the bigger one of the two, just based on my picture, because 2019 squared is bigger than 1867 squared. Could we do something like that? 2019 squared minus 1867 squared is b squared plus c squared minus a squared plus b squared, so the b's cancel out. So c squared minus a squared, which if I add 2a to both sides, or 2a squared to both sides, should be c squared plus a squared, which is x squared. Again, a has to be positive, so 2a squared has to be positive. So I definitely know for a fact that x squared has to be greater than the difference of these two squares. And we can work that out as well. So just over 500,000. And again, if I square root, I should be able to get sort of a lower bound. So 768.55 has to be less than x squared, or it has to be less than x. And, well, x is an integer, so just round up. So x has to be in that range. And if we put these two together, it was 27. Was it also 69? 49. I don't know. So I think any x in this range should work. Now what we might want to do is double check, especially if we've got time. If we don't have time, I'm pretty confident in how this worked out. So how many x's are in this range? Let's just quickly answer that before I do a little double check. So number of x's in an inclusive range, you take the big number, subtract the small number, and you add on 1. So I get 1980 plus 1, 1981. So I think that's our answer. Let's see if that is one of the answers, or maybe I've missed another condition or something like that. No, that would be answer E, which is kind of nice. But we could double check. Okay, maybe x is 769. I would just double check the extremes, really. I'll do this kind of quickly, but I'm confident in my answer. I'm glad that I mean, based on the answers, well, we might be off by 1 or 2, but I think we're good. What do we have? B squared, C squared, A squared, B squared. So 2A squared plus, well, actually, I can do this quickly. Add them all up. Add up all the squares. So 769 squared plus 1867 squared plus 2019 squared is 8,153,411. Divide by 2, some horrible little number, that gives me the sum for all of these. And now if I want to, I can solve for each square. And this should be bigger than the biggest square, otherwise 4076361. So I can definitely subtract that. This is b squared, c squared. So I can figure out a squared must be 344.5. And so we can quickly find an a from there. We should be able to get a b and a c. So it looks like everything is working out. We could solve them. I'm not going to, because I'm really happy with my answer there. I'm happy with the Cayley for the most part. I'd say it was an interesting paper this year. If you're looking for something a little simpler, I would recommend the 2019 Pascal. If you're looking for something a little harder but still multiple choice, I'd recommend the Fermat 2019. It's aimed at a grade 11 level. If you're looking for more grade 10 material, you're more than welcome to check out the Galois paper, as it's also aimed at grade 10, but it's got written solutions, so it's something a little different. But if you just want more Cayleys, I've got tons of them, so feel free to poke around the channel. Thank you guys so much for watching, and I will see you for more math in the future.